A judge model can catch subtle mismatches, but it costs tokens and can reflect prompt bias. You'll see how to connect the pieces into a workflow that compares two factuality checks and chooses the safer, cheaper one. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Hallucination detection is a practical safety step. You want to stop unsupported claims before they reach users. Two common ways people do this are NLI, a fast local classifier, and a judge-style LLM that applies a human-like rubric. NLI gives cheap, repeated checks at low latency. A judge can catch subtle context mismatches, but it costs tokens and can reflect prompt bias. Real teams care about two numbers: how often the detector ranks bad answers higher than good ones, and how many bad answers slip through as supported. That is the comparison we will measure. The intuitive idea is simple. Build a tiny labeled set of context, answer, and a binary label for unsupported or not. Run DeBERTa as an NLI detector to get a hallucination score. Then run an OpenAI judge prompt that outputs an unsupported score plus usage. Compare ranking quality and false negatives, and add a token cost signal for the judge. Strength of NLI is speed and determinism. Strength of a judge is nuance at higher cost. Project preview. We will assemble a tiny benchmark. Score it with DeBERTa MNLI. Evaluate ranking and false negatives. Then call an OpenAI rubric-based judge and compare AUROC and false negatives plus API cost. This keeps the comparison concrete and actionable before you scale. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To measure detectors, we need a tiny labeled benchmark that we can inspect quickly. This snippet creates the smallest labeled benchmark we can evaluate repeatably. Each row carries an ID, a source context, an answer, and a binary label, where 1 means the answer contains an unsupported factual claim. The examples are intentionally short, so engineers can inspect every failure case instead of trusting a hidden dataset. The labels list becomes the shared ground truth for every detector that follows, which keeps the comparison focused on detector behavior rather than changing inputs. The visible output confirms the benchmark size and class balance, so later AUROC and false negative numbers have a clear denominator. This small table is what we will feed into both detectors and use to examine exact misses. We need a reliable NLI baseline before adding expensive judges. This code runs a DeBERTa MNLI model through Hugging Face transformers to score answer support. The key move is pairing CTX and ANDs in auto-tokenizer.from pre-trained, then reading the entailment probability from auto-model for sequence classification.from pre-trained. Because the benchmark label is unsupported, NLI score returns 1 minus the entailment probability, so higher scores mean more suspected hallucination. Torch.noGrad keeps this in evaluation mode and avoids storing gradients we do not need. The printed NLI first checks the scale on a supported answer, while NLI-MS gives a first latency baseline for later comparison. You see numeric outputs, so we know the score range, and a per query time to compare against the judge API. Now that we have scores, we need evaluation metrics that matter to product teams. This example turns raw detector scores into decision metrics engineers can track across runs. AUC ranks every answer by NLI scores and measures whether unsupported answers generally receive higher scores than supported ones. AUC is the area under the receiver operating curve, a ranking measure of separability. The code then applies a simple threshold at 0.5 and counts false negatives as unsupported answers that were classified as supported, reported as NLI_FN. That false negative count is often the more painful number for hallucination detection, because those are the claims a product might pass downstream. The visible output shows both the ranking quality and the concrete miscount, giving the DeBERTa baseline a repeatable evaluation surface and something you can optimize against. If DeBERTa misses subtle context, we can try a rubric-based judge from OpenAI, but cost matters. This snippet adds a rubric-based OpenAI judge for the same benchmark row. OpenAI is accessed through OpenAI, and client.response.create sends the context, answer, and rubric as one compact prompt. The judge function returns both the unsupported score and token counts, because evaluation quality alone is not enough when a detector may run thousands of times. Temperature equals 0 is used to reduce sampling variation, but the rubric and model can still need validation on your own domain. The output shows one judge score plus usage, which sets up cost-aware comparison rather than a vibes-based choice. Watching token counts alongside the score helps budget realistic deployments. We now run the judge across the whole benchmark and compare directly to DeBERTa. This code completes the mini baseline by running the OpenAI judge over every benchmark row and comparing it with DeBERTa. Judge runs stores the score plus usage from each client.responses.create call. Then the same AUC function and false negative threshold are applied to judge scores. The pricing calculation uses token counts from res.usage and reports only the OpenAI API token cost. Local DeBERTa hardware cost is intentionally outside this tiny benchmark. Best is conservative. DeBERTa wins only when it is not worse on AUROC and false negatives. The output summarizes the trade-off in one line, making repeated experiment tracking straightforward. This final run produces 3 things you can act on: rank quality, false negative safety, and token cost per run. Mapping to a real project is straightforward. Replace the tiny benchmark with a sampled slice of a production FAQ or recent support tickets. Keep labels human inspectable and use the same rubric prompts you plan to deploy, so the judge evaluation matches live behavior. What you just learned in short: it is a benchmark-driven comparison between local NLI and an LLM judge. Use the NLI path when you need low cost and repeatable behavior. Use a judge when nuance matters and you can afford token cost. One caveat: judges can bias decisions through prompts and still miss domain-specific facts. So validate on ground truth. If you want a concrete next improvement, tune the decision threshold used to count false negatives for both detectors on a larger held-out slice of your logs, and track how that threshold affects false negatives and API tokens per 1,000 queries. That single parameter will directly trade safety against cost. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.